Hello and welcome back to the Quantum Slumber, where the deepest ideas in physics are told gently, like a late-night story, with room to breathe. Have you ever wondered how the sun can shine for billions of years without burning out? Or how your phone can remember a photo years later while it's completely powered off? Or how something as small as an electron can face a solid barrier and still appear on the other side, as if the wall briefly forgot to be a wall. In the world we live in, those ideas should feel impossible. A tennis ball doesn't pass through brick. A locked door doesn't open for free. A barrier is a barrier. And yet, at the quiet scale beneath our senses, the universe plays by a softer rule. Tonight, that rule has a name: quantum tunneling. And what makes this feel especially real, especially current, is that in October 2025, the Nobel Prize in Physics honored experiments showing that tunneling and quantized energy aren't just abstract math on a chalkboard. Under the right conditions, these quantum effects can appear in systems we can build, measure, and hold in our hands, like little pieces of the quantum world brought up to human size. That's the promise of our time together tonight. Not a lecture, not a test. Just a slow, careful journey until something that once sounded like quantum magic starts to feel strangely natural. If you enjoy calm science that helps you unwind, you can take a second to like, subscribe, or leave a simple comment. Maybe the most impossible thing you've ever heard about the quantum world. It helps this quiet corner reach other curious minds too. And now, let your shoulders drop, let your jaw unclench, let your breathing slow down, just a little. You don't need to memorize anything tonight. Just listen, because we're about to begin with the wall your intuition trusts the most, and the strange way the universe sometimes slips right through it. A wall is one of the few things your mind trusts without negotiation. You don't have to be a scientist to predict what happens next. You can feel it in your bones. Picture a simple brick wall, old bricks, solid mortar. No cracks you can see, no hidden door. Just that blunt, stubborn surface that tells the world, no. Now imagine a tennis ball in your hand. You throw it at the wall. It hits, and it bounces back. You throw it again. Same result. Again, same result. 100 times, 1,000 times, 1,000,000 times. The details might change. How fast you throw, the angle, the little scuff marks on the ball, but the conclusion doesn't. The wall stays the wall. The ball stays on your side of reality. That's classical certainty, the comfort of everyday physics. It's how your brain keeps you alive, by learning which barriers you can trust. And then, imagine something your intuition refuses to rehearse. Imagine the same tennis ball traveling toward the same wall. No drilling, no cracking, no explosion, no visible hole, no force pushing it through. It doesn't climb over, it doesn't squeeze around the edges, it doesn't break the bricks apart. It simply appears on the other side, intact, as if the wall had been solid a moment ago. And then, for a fraction of a heartbeat, the universe chose a softer rule. If that image feels absurd, that's exactly the point. In the world of our eyes, it is absurd. But in the world of atoms, where objects aren't chunky and definite in the way we imagine, this kind of event is not only possible, it's routine. That quiet passing through is what we call quantum tunneling. And the most important thing to understand about tunneling is this: it isn't a trick. It isn't a particle finding a secret crack. It isn't matter turning into a ghost. It's a consequence of what a particle really is, down at the scale where nature stops behaving like a set of hard marbles and starts behaving like a set of possibilities. Here's the gentle version. In everyday life, we treat objects as having one location at a time, one trajectory, one clear path through space. When something hits a barrier, it stops or it bounces. End of story. But at the quantum scale, a particle isn't best described as a tiny dot with a tiny address. It's better described as a spread of potential, a presence that can extend into space like a faint mist of probability, strong in some places, weak in others. Not because it's vague or unreal, but because reality at that scale is written in chances. So, when a quantum particle approaches a barrier, It doesn't behave like our tennis ball. It doesn't slam into the wall and rebound with perfect certainty. Instead, its presence, that spread of probability, can leak a little way into the forbidden region, into the place where, by classical rules, it should not be. Most of the time, nothing dramatic happens. The particle is found back on the original side, just as you'd expect. But not always. If the barrier is thin enough, if the conditions are right, there can be a small but genuine chance that the particle is found on the far side. No cracked bricks, no broken lock, just a change in where the universe allows the particle to be. That's tunneling, not a guarantee but a non-zero chance. And non-zero is the word that changes everything. Because the quantum world is a world of relentless repetition, countless particles, countless encounters, over and over, second after second. A probability that feels tiny to the human mind becomes inevitable when nature runs the experiment enough times. This is why tunneling isn't science fiction. It's reliable physics. It can be engineered, it can be predicted, it can be measured. It's the kind of strangeness that shows up not as a rumor, but as a current in a circuit, a number on a display, a technology that works whether or not we feel emotionally ready to accept it. And if the idea still feels strange, that's not a failure of understanding. It's an honest reaction to the gap between the world your senses evolve for and the world that actually runs the machinery underneath. Strangeness here is not a warning sign. Strangeness is the doorway, because tunneling asks you to relax a very old assumption that forbidden means impossible. Classical physics treats a barrier like a verdict. Quantum physics treats a barrier like a question. Not can you cross, but how likely is it really? There's another way to hold it in your mind if you want something calmer than tennis balls and bricks. Think of a hill you don't have the energy to climb. In daily life, you stop. You roll back. That's the rule. In the quantum world, the you approaching that hill isn't a single point. It's a spread. And part of that spread can reach beyond the crest, even when the energy isn't enough to earn the crossing in the classical sense. So the particle doesn't need to be strong enough to go over. It only needs the universe to allow a small chance of being found through. And that subtle shift from certainty to probability is the heart of tunneling. It's also why tunneling doesn't let you walk through walls in your everyday life. Your body is made of an unthinkable number of particles, and the walls you touch are thick on the quantum scale. The probabilities collapse into practical zero. The universe does not routinely grant macroscopic miracles. Not because it's cruel, but because the numbers are overwhelming. For large objects and thick barriers, tunneling becomes so unlikely that you can treat it as never. Your intuition survives. The wall stays a wall. But for electrons and atoms, facing barriers only a few atoms wide, unlikely happens all the time. And that's the flip that makes this phenomenon so eerie and so useful. The rule never changes. Only the scale does. So here's the small recap to let it settle. In classical life, walls are absolute. They are certainty. In quantum life, walls can be negotiable, not by force, but by probability. And once you accept that difference, even gently, you're ready for the next thought. Because if particles can slip through barriers in miniature, then some of the biggest, most dependable miracles in our universe begin to make a different kind of sense. To see why this matters, we have to go bigger than any wall on Earth. If you hold that image of a wall in your mind for a moment, solid, unquestioned, dependable, there's a place where that certainty quietly fails every second of every day. Not here on Earth, not in a laboratory, but deep inside the sun. From the outside, the sun looks simple, a steady light, a warm circle that rises and sets, a familiar clock in the sky. But inside, the sun is a crowded ocean of particles, mostly bare nuclei and free electrons, moving in constant restless motion. In that plasma, protons are everywhere, and protons all share the same electric charge, positive. That single fact creates a profound problem. Positive charges repel, not like a preference, not like a gentle push, like a rule that refuses to negotiate. When two protons drift toward each other, they begin to feel an increasing resistance. The closer they get, the stronger the repulsion becomes. It rises fast. It rises sharply. It rises like a steep hill that gets steeper the closer you climb. Physicists have a name for this barrier, the Coulomb barrier. But you don't need the label, you only need the picture. Two protons want to fuse, but between them is an invisible hill of electric repulsion. Now here's the strange twist. Fusion is not an average distance kind of event. It's an extremely close kind of event. There is another force in nature, the strong nuclear force, that can bind particles together with astonishing strength. It is the force that holds atomic nuclei intact. It is powerful enough to overcome the electric repulsion once the protons are close enough. But the strong force is very short range. It does not reach out across space like gravity. It does not lean across the table. It waits until you are almost touching. So, the situation inside the sun is quietly dramatic. The sun is full of protons, forever bumping, forever swirling, forever colliding. But for fusion to happen, two protons must come extremely close enough for the strong force to grab them and hold them together. And to get that close, they must somehow pass the electric barrier that tries to keep them apart. If you think in classical terms, the story sounds almost impossible. Classically, a proton is like a tiny ball. It has a position, it has a speed, it has an energy. If it doesn't have enough energy to climb over a hill, it rolls back down. If it runs into a wall, it bounces away. So imagine two classical protons approaching each other in the sun's core. They rush together, drawn by random motion and immense pressure. They get close. Then the electric repulsion rises, and rises, and rises. And if they don't have enough energy to crest that hill, they are turned back. They separate, they move on, the moment passes. In a purely classical universe, that would be the end of it. And if that were truly the rule, the sun's steady glow would become hard to explain. Because even though the sun's core is hot, unimaginably hot by everyday standards, classical calculations say that most protons still do not carry enough energy to regularly overcome the Coulomb barrier. They're energetic, yes, but the barrier is steep. So, how does the sun keep shining calmly and continuously for billions of years? This is where quantum tunneling stops being a weird trick and becomes something far more beautiful. A quiet permission slip written into reality. In the quantum view, a proton is not only a little ball with a definite path, it also behaves like a wave. Not a water wave, not a sound wave exactly, but a wave of possibility. A spread out presence that describes where the proton could be found if you looked. And waves do something that classical balls never do. A wave can press into a region it doesn't have the energy to fully occupy in the classical sense. It can leak. It can fade. It can extend into forbidden places, not with full strength, but with a dwindling trace. So, when a proton approaches the Coulomb barrier, the quantum story is not simply, it either goes over or it turns around. The quantum story says, there is a small chance it appears on the other side. Not because it smashed through. Not because the barrier cracked. Not because the proton cheated. But because the wave-like nature of matter makes the probability of crossing not exactly zero. That crossing is tunneling. And tunneling is the reason the sun is not a paradox. Because the sun does not require tunneling to happen often. It only requires that it happens sometimes. And it has something that makes sometimes powerful. Numbers, scale, repetition. The sun's core contains an ocean of protons. They collide constantly. They approach one another constantly. They attempt the impossible constantly. Most attempts fail. Most close approaches end the same way, a bounce apart under electric repulsion. But if the chance of tunneling is even slightly above zero, then over enough attempts, those rare successes become guaranteed. A tiny probability, repeated countless times, becomes certainty. That phrase sounds like philosophy, but it's really just the logic of large numbers. If an event has a 1 in a trillion chance, you don't expect to see it in a small room. But if the room contains more than 1 trillion trials, it becomes part of the routine. Inside the sun, nature runs that kind of routine continuously. Deep in the sun's core, you can imagine a kind of quiet lottery. Not a dramatic one, not one with a ringing bell, just a calm, relentless drawing of tickets. Protons approach, they separate. Protons approach, they separate. Protons approach, they separate, and then every so often one doesn't. It doesn't climb over the hill. It doesn't batter the hill down. It simply shows up beyond it, close enough for the strong force to take over, close enough for fusion to begin. And once fusion begins, the sun's entire character follows. Because fusion does not just create new nuclei, it releases energy. The main pathway in the sun is often described as the proton-proton chain, and you do not need to memorize its steps, you only need to feel what it means. In broad strokes, protons slowly become helium. It takes multiple interactions with intermediate particles and transformations along the way. It is not a single clean slam together. It's a patient sequence. But the essential result is this. 4 protons can ultimately become one helium nucleus, and the final helium nucleus has slightly less mass energy than the starting protons did. That difference is not lost. It becomes energy carried away in different forms, gradually reshaped into heat and light. That energy works its way outward through the sun's interior. It scatters again and again. It wanders. It gets delayed. It gets rerouted. And eventually it escapes as sunlight. So, when sunlight lands on your skin, it is the end of a long journey that began with a forbidden event. A barrier crossed without force. A wall slipped through without breaking. Quantum tunneling is not a footnote in that story. It is the opening move, and there is something deeply calming about that, if you let it settle, because it means the sun is not powered by violence alone. It's powered by persistence, by tiny chances, by endless tries, by the universe doing a quiet thing repeatedly until a steady glow emerges. It also means something else. It means the impossible is not always a hard no. Sometimes it is a soft maybe. And a soft maybe, in a big enough universe, becomes yes. This is the point where many explanations try to get louder, more technical, more crowded with equations. But we can keep it simple. There is a barrier. Classically, the barrier is too high. Quantum mechanically, the barrier is not perfectly sealed. A small probability leaks through. The sun has more trials than we can intuitively imagine. So the sun's steady light becomes natural, not magical, not lucky. Just the expected outcome of a rule that is slightly different than our everyday instincts. And once you see the sun this way, once you realize that one of the most familiar things in your life depends on quantum tunneling, it changes the feeling of the concept. Tunneling is no longer a strange stunt. It becomes a gentle explanation for why reality is as stable as it is. Without tunneling, the sun would not shine the way it does. And without the sun shining, there is no warmth on Earth. No growing seasons. No oceans kept liquid. No long biological story unfolding over time. No you listening right now. So, when we say tunneling helps the sun shine, we are not just telling a neat science fact. We are describing one of the quiet supports holding up your entire world. And that makes the next thought almost unavoidable. If nature uses tunneling to power a star, then tunneling is not rare. It is not exotic. It is not locked away behind laboratory doors. It is a working feature of the universe. And once something is a working feature, engineers eventually learn to work with it on purpose. They learn to build devices that invite that soft maybe to happen exactly when they want it to. They learn to turn the impossible into a tool. And then we come back down to Earth, back to your pocket. From the deep heat of the sun's core, it's almost funny how quickly the same idea returns to something ordinary. Because quantum tunneling isn't only a cosmic solution to an invisible problem, it's also the quiet reason your phone can keep a memory while it sleeps. Think about what your phone is asked to do, not just for an hour or a day, but for years. A photo you took on a random afternoon can still be there long after the battery has drained. A note you typed half awake can still be waiting after hundreds of shutdowns. A password, a voice memo, a favorite song, still intact. In a world of simple switches, that shouldn't be possible. A switch is either on or off. and when the power is gone, the on disappears with it. So modern devices rely on a different kind of memory, one that doesn't need electricity flowing through it every second to keep its state. It needs a place to store a physical difference that remains even in darkness. And the surprising truth is that much of our everyday memory is not stored as energy. It's stored as charge. In the heart of flash memory, used in phones, SSDs, USB drives, cameras, there's a tiny structure that acts less like a light switch and more like a sealed jar. A place where electrons can be put away. A place where they can be held. A place where they can be counted. It's called a floating gate, or in newer designs, a charge trapping layer. But again, you don't need the vocabulary, you need the mental picture. Imagine a microscopic island, an isolated region inside the device, surrounded by insulating material like glass. Electrons can't just casually wander in or out, because the insulator is meant to be a barrier. So, when the device is powered off, those electrons stay where they are. And that where they are becomes the memory. Because in electronics, an extra pocket of electrons changes how a transistor behaves. It shifts a threshold. It changes when the transistor decides that a voltage counts as a yes or a no. In a gentle sense, the device isn't remembering a photo as an image. It's remembering it as a vast arrangement of tiny, more charge and less charge, arranged in patterns so dense you never have to see them. Your photo becomes a landscape of stored electrons. Your message becomes a pattern of trapped charge. Your memories become literal, physical arrangements in silicon. And now the question becomes unavoidable. If electrons are trapped behind an insulator, how do we ever put them there in the first place? How do we write data into a sealed jar? This is where engineers learn to make the impossible practical. They learn to build a barrier that is real, and yet not perfectly final. In many flash memory designs, the insulating layer is extremely thin enough that under the right conditions, electrons can tunnel through it. Not by smashing it, not by melting it, but by using a strong electric field to shape the electron's quantum behavior, to encourage a small chance into a reliable event. If you want a clean image, picture a hill and a wind. The hill is the barrier. The wind is the electric field. You're not lowering the hill to zero. You're tilting the landscape enough that the electron's wave-like nature can leak across in a controlled way. This is one of the most beautiful themes in modern technology. We don't always defeat nature's rules. Sometimes we cooperate with them. So a flash memory cell has two key jobs. It must be able to store charge for a long time, and it must be able to move charge in and out when asked. Storing charge is the easy part, at least conceptually. If the electrons are trapped behind a good insulator, they can remain there without power, sometimes for years. But moving them in and out is where the design becomes almost poetic. When your phone saves something, it is not simply writing in the way you write ink onto paper. It's placing electrons onto that isolated island. And when your phone deletes or overwrites something, it is not scrubbing ink away. It is pulling electrons off that island, returning the transistor to a different threshold. That's how a memory becomes a choice. A 0 or a 1 in many designs is the floating gate charged or not charged? Or more subtly, how charged is it? Because modern flash often stores more than 1 bit per cell by using multiple charge levels, tiny steps of a little, more, even more, each step corresponding to a different threshold. And that's a good moment to pause and appreciate how strange our world really is. A photo of a sunset can be stored as a careful arrangement of electron populations. A movie can be stored as charge levels measured in microscopic transistor behavior. A decade of digital life can be carried in your pocket because we learned how to trap electrons and release them without breaking the walls that hold them. But flash memory does not work by luck. It works by engineering the probability until it behaves like a tool. In the quantum world, tunneling starts as a rare event, something that can happen but usually doesn't. In a device, usually doesn't is not good enough. Usually is not a guarantee. Usually doesn't save your files. So, engineers shape the situation until the tunneling rate becomes predictable. They do it with geometry, with materials, with fields. They do it by choosing how thick the barrier is. Because in tunneling, thickness matters in a way our everyday intuition isn't trained for. If you make the insulating layer just a little thicker, the tunneling probability can collapse dramatically. If you make it just a little thinner, the probability can surge. Small changes can create huge differences. That's why flash memory design is always a balancing act between two desires that compete. You want the electrons to stay put for years when you're not writing, but you also want them to move quickly when you are. You want stability, and you want speed. So, the barrier thickness, the material quality, and the applied voltages become a kind of negotiation between patience and responsiveness. And that negotiation shapes the feel of your device. It shapes why some drives are fast, why some are long-lasting, why some wear out sooner. Because there is also a quiet cost to forcing electrons through barriers again and again. Every time you write and erase, you stress the insulating layer. Over many cycles, tiny defects can form, traps can appear, the barrier becomes less perfect. This is one reason flash memory has a limited number of write cycles. Not because the idea is fragile, but because the materials are doing something extraordinarily subtle at massive scale, over and over, until microscopic wear begins to matter. And even that is strangely comforting if you think about it, because it means the limits of our devices are not arbitrary. They are the limits of matter, faithfully expressed. So, when you save a photo and your phone doesn't even hesitate, there is a hidden choreography happening beneath your screen. A voltage is applied, an electric field builds across an insulator so thin it almost feels like a dare. Electrons, waves of possibility, are encouraged to cross a region they are not supposed to cross. Charge accumulates on an isolated island, and then the device relaxes, turning the barrier back into a keeper. Your memory becomes a trapped imbalance that stays there quietly without needing power to hold it up. That's why flash memory is called non-volatile. It doesn't evaporate when the electricity leaves. It remains. And if you hold that picture gently, the phrase, "a controlled impossible," stops sounding like a metaphor. It becomes literal. Every text you've kept, every photo you've saved, every app you've installed, all of it depends on electrons behaving in a way that classical intuition would call wrong. And yet it works so reliably that most of us never even think to be surprised. That reliability is important for another reason. Because people sometimes hear quantum and imagine chaos, randomness, uncertainty, things that can't be trusted. But the modern world is built on quantum effects that are trusted so deeply we stake our lives on them. Not because they are mystical, because they are consistent, because the rules are strange but stable. And the deeper you go into physics, the more you realize strangeness and reliability are not opposites. They're often partners. So, when you look at your phone, you can see it as a practical object, a tool, a habit, a distraction. But it is also something else. It is a small museum of quantum behavior, a quiet exhibit of tunneling engineered into usefulness, a reminder that the universe is not only grand in the sky, it is also intimate in your hand. And if tunneling can be harnessed this way, if it can be used to store your life in little pockets of charge, then the next step in understanding it becomes almost irresistible. What is an electron really that it can behave this way? What kind of thing can face a barrier and still leave a trace beyond it? What kind of object doesn't merely collide with a wall, but spreads into it? Because the real secret is that an electron isn't only a particle. When people first hear the phrase quantum tunneling, it can sound like a trick, like the universe is cheating, like an electron is doing something it shouldn't be allowed to do. But the deeper story is quieter than that. The electron isn't breaking the idea of a wall. It's revealing that, at its scale, the electron was never just a tiny marble to begin with. It is also a wave, and once you let that thought settle, slowly, without forcing it, the rest starts to feel less like magic and more like a kind of strange honesty. Because waves don't behave the way little hard objects behave. A wave can spread out. A wave can overlap with itself. A wave can slip into places you wouldn't expect, not by smashing through, but by being there a little already. So to understand tunneling, we need one gentle shift in how we picture things. Not everything you know gets replaced, but one piece gets softened. And we can start with the most familiar messenger in physics, light. For a long time, humans were comfortable thinking of light as a wave. It bends around edges. It spreads out from a source. It makes interference patterns, those alternating bright and dark bands that appear when waves overlap and either reinforce or cancel each other. If you've ever seen ripples on a pond, you already understand the basic mood of a wave. Two ripples meet, and the surface doesn't choose one ripple or the other. It adds them together. The water simply does what water does. And light, in many experiments, behaves just like that. One of the most famous is the double-slit experiment. You shine light at a barrier with two narrow openings, and you let it land on a screen behind it. If light were only a stream of tiny pellets, you'd expect two bright stripes, one stripe behind each opening. But that's not what happens. What appears is an interference pattern, a series of bands bright and dark, like the light is rippling, like it's passing through both openings and overlapping with itself. The bright regions are places where the wave crests line up. The dark regions are places where a crest meets a trough, and the waves cancel. It's the signature of something spread out. A wave that can take multiple paths and still remain one coordinated thing. So far, so good. The universe seems perfectly content to let light be a wave, until it suddenly isn't. Because when scientists began probing how light interacts with matter, another side of the story showed itself. Light can arrive in discrete packets. Not a continuous smear of energy, but little bundles. The photoelectric effect made this hard to ignore. Shine light on certain metals and electrons pop out, but not just with any light. There's a threshold, a minimum frequency, and above that threshold, the energy of the ejected electrons depends on the light's frequency, not merely its brightness. In other words, it wasn't behaving like a smooth ocean washing up on shore. It was behaving like a rain of indivisible drops, as if light carries its energy in portions you can count. Those portions are what we call photons. And now we're in the first soft paradox. Light spreads like a wave and arrives like a particle. Not sometimes. Both are real aspects of how it behaves, depending on how you ask the question. And physics, instead of choosing one picture and throwing away the other, learns something more subtle. The picture you use depends on the kind of measurement you make. Reality, at this scale, refuses to stay inside one human metaphor. That could have been the end of it, a strange quirk of light. But then matter entered the story, and the universe became even more quietly astonishing. In the 1920s, Louis de Broglie suggested something that sounds almost too simple now, but at the time was a deep twist. If light, something we once thought of as a wave, can behave like a particle, then maybe particles, things we think of as little objects, can behave like waves. Maybe a particle like an electron has a wavelength, a real one, not a poetic one. A measurable one. And this idea didn't stay philosophical for long. Electrons were fired at crystals, and what appeared on the detector was not the blotchy pattern of tiny bullets hitting a target. It was diffraction, interference, a wave signature. A crystal is like a repeating array of atoms, like a set of evenly spaced grooves. If a wave encounters something like that, it can scatter in a structured way, producing patterns that reflect the spacing inside the crystal. And electrons did exactly that. They produce patterns that only make sense if the electrons were behaving like waves passing through a regular structure. Not because the electrons were being guided by something external, like a hidden set of rails, but because the electrons themselves have a wave nature. They can spread, they can interfere, they can diffract, they can act in certain conditions like a cloud of possibility rather than a bead of matter. So, now we have a new kind of object in our story. Not a wave in the classical sense, like a vibrating string. Not a particle in the classical sense, like a grain of sand. Something that uses both behaviors, depending on the situation. And the name we give to the most useful description of this strange object is the wave function. That word can feel intimidating, but the concept we'll use tonight is gentle. A wave function is not the electron itself in the ordinary sense. It is a description of what the electron is likely to do. It's a way of encoding the spread of possibilities. If you want a calm mental image, Picture a soft fog around where the electron might be. Not a fog of material stuff, a fog of probability. In some regions, the fog is thicker. In others, it is thin. And where the fog is thick, the electron is more likely to be found if you measure it. Where the fog is thin, it's less likely. And then comes one of the simplest but most powerful rules in quantum mechanics. The probability of finding the particle in a given place is related to the square of the wave function's amplitude there. You don't need the equation, you just need the feeling. The wave function has a kind of height, an amplitude, like any wave. And probability is connected not to that height directly, but to its squared magnitude, which in practice means probability behaves like a physical intensity, like brightness, like density. A small amplitude becomes an even smaller probability when squared. A larger amplitude becomes a much larger probability. This squaring is one reason quantum patterns can be so sharply defined, even though the underlying wave function can be spread out. So, now we can return to the double-slit experiment, but in the gentlest possible way. Imagine you fire electrons one at a time through two narrow slits. If electrons were only particles, you'd expect two piles behind the two slits. But you don't get that. You get an interference pattern, even when the electrons are sent one by one, which forces a quiet conclusion. Each electron, in some meaningful way, behaves like a wave passing through both paths and interfering with itself. And then, when you detect it, it arrives as a single localized event. One dot on a screen. Not a smear, not a half dot, a dot. Do this enough times and the dots form a pattern that looks like a wave, a pattern that grows out of many single events. This is the strange rhythm of quantum physics. Spread, and then, when you look, a point, possibility, and then an outcome. And the wave function is the tool that holds that rhythm without breaking. It tells you how the possibilities flow, how they overlap, how they add and cancel. It gives you the map of might. It does not always tell you which specific is will appear on any one run. That's not a weakness. That's a feature of the world at this scale. Now, you might be wondering something very human and very reasonable. If the electron is a wave, what is it made of? What is actually waving? In classical waves, something physical is oscillating. Air pressure, a string, the surface of water. In quantum waves, the wave function isn't a physical displacement in space like that. It's a mathematical object that encodes probability. And that can feel unsatisfying until you remember something important. Physics is not obligated to feel like common sense. Physics is obligated to predict what happens. And the wave function predicts, with extraordinary accuracy, the patterns we see. If you use it correctly, it tells you how likely you are to find the electron in this region versus that region. It tells you the structure of energy levels in atoms. It tells you why some transitions happen and others don't. It tells you the shape of chemical bonds. It tells you, eventually, why tunneling occurs. So, even if the wave function isn't a wave of stuff like water, it behaves like a wave in the way it spreads and overlaps. And that wave behavior is not optional. It shows up in experiment after experiment. So, we accept it not as a fantasy but as a faithful description. Now, let's gently touch the idea that makes many people uneasy: superposition. This word sometimes gets dressed up in dramatic ways, but we can keep it simple. Superposition is just the fact that waves can add. If you have one wave pattern and another wave pattern, you can combine them and get a new pattern. That's how interference happens. In quantum mechanics, the wave function for a particle can be a combination of possibilities. Not because the particle is trying to trick you, but because the mathematics of wave behavior naturally includes combinations. So before measurement, the electron's wave function can be spread over multiple positions, multiple momenta, multiple paths. Then when an interaction occurs that counts as a measurement, when the electron is forced to leave a definite trace in a device, the outcome becomes specific. You find it here, not there. And the distribution of those outcomes over many trials matches the probability pattern encoded by the wave function. That's the practical core. You don't have to decide tonight what you believe about collapse or interpretation debates. Those can be fascinating, but they're not necessary for understanding tunneling. All you need is this: an electron behaves like a wave of probability, and probability waves can extend into regions that a classical particle would never enter. This is where the word barrier begins to soften. In classical life, a barrier is a hard boundary, a cliff edge, a locked door, a wall. On the quantum scale, a barrier is often better pictured as an energy landscape, like a hill. If a particle has less energy than the hill's height, classical thinking says it cannot cross. It would have to climb higher than it can, so it stays trapped. End of story. But a wave doesn't behave like a single point trying to climb. A wave can extend. It can spread into the region of the hill even if it cannot classically exist there. And inside that region, something subtle happens. The wave doesn't keep oscillating the way it does in allowed regions. It decays. It becomes smaller as it goes deeper. Not because the wave has been destroyed, just because the barrier is suppressing it. So, the wave function can seep into a forbidden region the way a sound can seep through a wall. Not fully, not loudly, but not as a strict zero either. And if the barrier is thin enough, the wave function can still have a small presence on the far side. Which means the probability of finding the particle on the other side is small, but not zero. And there it is. That's tunneling. Not an electron ramming through a wall like a ghost. Not the universe temporarily forgetting its own rules. Just wave behavior taken seriously. A small probability leaking into the forbidden region. A small probability emerging on the other side. And if you run the experiment enough times, small probability stops being a curiosity and becomes a steady phenomenon. This is the same logic we'll soon use for the sun. A single proton pair has a small chance to tunnel through the repulsive barrier and fuse. But the sun offers endless attempts, so small chances become reliable outcomes. And in your phone, the barriers are engineered so that the chances can be dialed up when you want to write, and dialed down when you want to store. The same physics, two very different moods. One cosmic, one personal. There's another gentle piece of clarity here. When we say electron as a wave, we do not mean the electron is smeared out like jam in space forever. We mean that the description of its possible locations is spread out until an interaction pins it down. And the more you constrain it, the less certain other things become. There's a deep trade-off in the theory that shows up in how sharply a wave can be localized versus how broad its momentum becomes. Again, you don't need formulas, just the feeling. A sharply confined wave contains many wavelengths mixed together, and that corresponds to a range of momenta. A more spread out wave corresponds to a more definite momentum. This is part of why barriers and confinement matter, and part of why a wall is not just a physical object, but a boundary condition shaping what kinds of waves are allowed to exist. So as we move forward, keep one image in mind: not a billiard ball, not a mystic spirit, a wave of possibility that can be compressed, stretched, redirected, and suppressed by the shapes of the world. Sometimes those shapes create stable standing patterns we call orbitals in atoms. Sometimes they create quantized energy levels. Sometimes they create the trapdoors that make your memory devices work. And sometimes they create the strange situation where a particle approaches a barrier and, instead of simply bouncing, it leaves a fading footprint inside it, a footprint that might reach the far side. This is why tunneling is not a special exception. It is what you should expect once you accept that the particle is also a wave. A wall is not merely a place where a particle stops. It is a region where the wave function changes its behavior. And that change, this gentle decay, sets the stage for everything that comes next. So, if the idea still feels a little unreal, that's okay. It is allowed to feel unreal, because it does not come from everyday experience. It comes from a deeper layer of reality we're not built to see directly. But it is also deeply consistent, and it is deeply testable, and it is the reason the next step will feel almost inevitable. Because once something is a wave, it doesn't slam into a barrier, it spills into it. A barrier feels like one of the most honest things in the world. A wall is a wall. A locked door stays locked. A cliff edge doesn't politely allow you to keep walking. And most of the time, physics agrees with that feeling. In the classical picture, a barrier is simple accounting. If you don't have enough energy to get over it, you don't cross. You roll up, you slow down, and you return. Nothing personal, nothing mysterious. But in quantum physics, the word barrier quietly changes meaning. It stops being a solid object you can touch and becomes a region where motion is not allowed in the usual way, an energy landscape, a hill in the invisible terrain. This matters because in the quantum view, a particle isn't only a point-like bead traveling along one definite path. A particle is described by a wave function, a spread-out mathematical presence that tells us where the particle could be found if we looked. And waves behave differently at boundaries than beads do. A bead hits the wall, a wave meets the wall and responds. It reflects, yes, but it also reaches into the barrier, just a little. That reaching in is the entire doorway to tunneling. To picture it gently, imagine walking toward a fog bank that grows thicker and thicker. The edge of the fog is not a hard line. You don't step from perfect clarity into perfect opacity. The fog starts thin, then it deepens. Your outline softens. The world becomes quieter. And if the fog bank is thin enough, you can still emerge on the far side, muted, but still there. A quantum barrier is not fog, of course, but it has something like fog's gradualness. The wave function doesn't slam into a barrier and stop like a marble. It changes character as it enters the forbidden region. Outside the barrier, the wave function can oscillate. It can ripple like a regular wave. That oscillation is tied to the familiar idea of motion. Inside the barrier, if the particle's energy is lower than the barrier's height, the wave no longer oscillates in the same way. It becomes what physicists call evanescent, a wave that fades as it goes. Its amplitude shrinks with distance. It doesn't march forward confidently. It thins out. And here is the quiet, astonishing point. If the barrier is finite, if it has a thickness, then a fading wave can still have a non-zero trace on the far side. Not much sometimes, just a whisper. But a whisper is not nothing. And in quantum physics, not nothing means not impossible. So, tunneling is not a particle breaking through a wall. It's not a particle smashing its way out, or finding a crack, or borrowing energy like a quick loan. Tunneling is the probability that comes from a wave function continuing through a region where it is fading rather than oscillating. You can hold that as a single sentence. A barrier doesn't always erase the wave function. Sometimes it only reduces it. And reduce does not mean zero. This is why tunneling depends so fiercely on thickness. Because decay is not gentle, it is exponential. Exponential decay is the kind of fading that feels unfair in a way. It means a small change in distance can create a huge change in outcome. Add a little width, and the wave function shrinks far more than your intuition expects. Remove a little width, and the surviving trace can jump dramatically. This is one of the reasons tunneling becomes so useful in technology, and so unavoidable in tiny electronics. A barrier that is just a few nanometers thicker might turn a noticeable tunneling current into something effectively absent. A barrier that is a few nanometers thinner might turn stable storage into constant leakage. Nature is precise that way. It doesn't give you half measures. It gives you a dial with an exponential slope. If you like having one quick formula moment, only to anchor the feeling, here's the gentle version. The tunneling chance falls off exponentially as the barrier gets wider. That means a tiny change in thickness doesn't give you a tiny change in outcome. It can give you a collapse. In the simplest models, scientists write this with an exponential e raised to a negative number that grows with the barrier's width. You don't need the symbols tonight, just the meaning. Make the barrier a little wider and the chance drops fast. And that one idea explains so much of what comes next. So then the next question arrives naturally, especially if you're half asleep and your brain is trying to protect the comforting rules of everyday life. If tunneling is real, why don't we see it all the time? Why doesn't a tennis ball sometimes appear on the other side of a brick wall purely by chance? The answer is calming because it preserves your intuition while still respecting quantum truth. A tennis ball is not a single coherent quantum wave. It's a vast collection of atoms, each interacting with the environment, each entangled with air molecules, vibrations, heat, light, and the countless little jostles that keep macroscopic objects behaving classically. Quantum effects like tunneling rely on a kind of delicate coherence, an ability for the wave-like description to remain meaningful across the relevant region. In a macroscopic object, that coherence is shredded almost instantly. The wave of might be becomes a messy cloud of almost certainly not, long before any dramatic tunneling could occur. And then there's the barrier itself. A brick wall is enormously thick on the scale that matters. Even a sheet of paper is thick. Even the thin skin of oxide in a microchip, tiny as it is still many atoms across. For tunneling, thick is not a matter of inches. It's a matter of how quickly the wave function decays inside the barrier. In everyday barriers, the decay length is so short that the wave function is extinguished long before it could reach the other side. So, the probability is not merely small. It is crushed, and that's why your world stays stable. That's why you can lean on walls, lock doors, and trust floors. Tunneling doesn't threaten the reality you live in. It only reveals that, beneath the surface, reality is governed by probabilities that become invisible at human scale. Now, there's another subtle piece that often gets overlooked. Tunneling is not only about crossing, it's about how often an attempt happens. If a single attempt has a tiny probability, repeated attempts can still create a reliable effect. The universe is patient like that. In a star, particles collide incessantly. In a solid, electrons are everywhere, constantly moving, constantly meeting potential barriers. In a nucleus, an alpha particle can knock against the edge of the nuclear potential again and again, like a trapped wave trying the boundary over and over. So, tunneling is not one dramatic leap, it's a statistical rhythm. A small probability, multiplied by an enormous number of chances, becomes an observable rate. That's how physics often speaks about tunneling in practice, not as a one-time miracle, but as a predictable lifetime, a half-life, a leakage rate, a current. It's a way of turning uncertainty into forecast. And once you begin thinking that way, tunneling starts to feel less like a violation and more like a method. A barrier is no longer a strict no. It is a how much and a how often. Now, let's bring it back to the heart of the idea, the barrier itself, because the word forbidden can make people imagine the wrong thing. When physicists say classically forbidden, they are not saying the universe refuses to allow this region to exist. They're saying a classical particle with this energy cannot have this kind of motion here. In classical mechanics, being inside the barrier would require an imaginary momentum, which is a polite way of saying the usual description breaks. In quantum mechanics, the wave function handles that break gracefully. It doesn't demand a particle-like trajectory through the forbidden region. It simply becomes a decaying shape, one that can, in principle, extend through. And this brings up a question that sounds philosophical, but is actually very practical. What is the particle doing inside the barrier? Is it moving there? Is it stuck there? Is time passing there in the same way? For now, you don't need the deep debates. For this moment, it's enough to hold a simple, usable picture. Inside the barrier, the particle's wave-like description is present but shrinking. It is not a classical journey. It is not a path you can trace. It is an amplitude that fades. And when the barrier ends, whatever amplitude remains can resume its usual oscillating form on the far side. Then you measure, and you find the particle either reflected back or transmitted through. That's the cleanest version. And there's one more gentle point that makes tunneling feel less like cheating and more like inevitable. In the quantum picture, a particle can be localized, found in one place when you look, but its wave function can be spread out. This is not optional. It's baked into the structure of the theory. So, whenever there is a finite barrier, there is always a possibility, however tiny, that the wave function extends beyond it. And whenever there is a non-zero amplitude somewhere, there is a non-zero chance of detection there. That's tunneling at its core, not a special exception. A consequence. A wall doesn't have to fail for tunneling to occur. Nothing needs to crack, no secret door needs to open, the barrier remains intact. What changes is your definition of crossing. Crossing is no longer a little object travels through the material. Crossing becomes the probability distribution has support on the far side. And once you accept that definition, once you let it rest in your mind, tunneling stops sounding like a magic trick. It becomes a very quiet kind of honesty. A reminder that at the smallest scales, certainty is not the default. Probability is. And barriers don't say never. They say rare, or often, or almost always not, depending on how thick they are and how many times the universe tries. Now that we know how it can happen, let's watch where nature uses it, quietly, constantly. Somewhere out beyond the reach of your senses, tunneling stops being a strange exception and starts feeling like a quiet habit of nature. Not loud, not flashy. More like a steady, patient way the universe does bookkeeping, when the classical rules would be too rigid. One of the first places you meet that habit is inside the heart of matter itself, and the part we usually imagine as sealed shut, the atomic nucleus. If you picture a nucleus the way old textbooks sometimes did, you might imagine protons and neutrons packed together like marbles in a jar, solid, contained, permanently locked in place. But the nucleus is not a jar. It's more like a landscape made of forces, a deep valley surrounded by steep walls shaped by the strong nuclear force that holds things together, and the electric force that pushes protons apart. For certain heavy nuclei, there's a peculiar arrangement. Inside the nucleus, an alpha particle, 2 protons and 2 neutrons bound together, can behave as though it's already formed, almost like a small cluster inside the larger whole. It isn't sitting there like a little pebble you could point to. It's a quantum presence, a pattern, a possibility that can become real when the conditions are right. And the conditions are odd, because if that alpha particle tried to leave the nucleus in the classical way, it would face a problem that feels absolute. The strong force holds it tight at short range. But once it tries to move outward, the electric repulsion between the positively charged alpha particle and the positively charged nucleus creates a barrier. A Coulomb barrier. High, steep, unforgiving. Classically, the alpha particle does not have enough energy to climb over that barrier and escape. And yet, some nuclei do decay. Not by breaking apart violently, not by gradually leaking like a cracked container, but by releasing alpha particles at a measurable, predictable rate for years or centuries or far longer. So, how does something trapped behind a barrier get out? This is one of tunneling's most beautiful signatures. It turns impossible into rare, and then it turns rare into a clock. Inside the nucleus, the alpha particle's wave function doesn't stop sharply at the barrier. It extends into the forbidden region, fading as it goes. Most of the time, that fading goes nowhere. The particle remains confined, but not always. Every so often, a tiny fraction of that quantum presence makes it through to the far side of the barrier, enough to count as an escape. Not because the particle gathered extra fuel, not because the barrier dropped, not because physics made an exception, simply because the barrier has a finite thickness, and the wave function is allowed to have a faint tail beyond it. When you zoom out and watch many nuclei over time, those faint tails become statistics, and those statistics become half-lives. That's the part that feels almost comforting. Radioactive decay is not random chaos. It is random at the level of a single atom, yes, but it is orderly in the large. A half-life is the universe saying quietly, here is how often tunneling succeeds. And the reason those half-lives can vary so wildly, from fractions of a second to times longer than civilizations, is the same reason tunneling can feel so sensitive and strange. Exponential decay. A small change in barrier width or height can create an enormous change in tunneling probability. In the nucleus, the barrier is shaped by charge, size, and energy levels. Adjust those slightly, and the odds of escape can swing dramatically. That's why some isotopes feel stable across a human lifetime, while others vanish so quickly you can barely prepare to measure them. It isn't that nature can't decide. It's that nature is being precise in a language that our everyday intuition doesn't speak. And if you sit with that for a moment, it becomes a gentle kind of awe. Deep inside matter, tunneling is one of the ways reality negotiates with constraints. Not by breaking them, but by slipping through the narrow places where probability still survives. Now, from the nucleus, dense, hidden, and ancient, tunneling reappears in a setting that feels almost opposite. Not deep inside matter, but in the tiniest gap between two surfaces. A gap so small that to your eyes, it wouldn't look like space at all. Just closeness. This is where the scanning tunneling microscope enters the story. Before the STM existed, seeing atoms sounded like a poetic exaggeration. We could infer them. We could measure their effects. We could map patterns indirectly. But to scan a surface and trace individual atoms like hills on a landscape, that felt like science fiction. The STM made it real by doing something that sounds impossible in plain language. It detects a current flowing through empty space. Here's the calm version of how. You take a needle-like metal tip, not a needle in the sewing sense, far sharper. A tip that ends in just a few atoms. You bring it extremely close to a conductive surface, not touching, just hovering above it, separated by a gap that may be only a nanometer or so. Then you apply a voltage between tip and surface. Classically, electrons should not cross that gap. It's vacuum, it's an insulator, it's nothing in the everyday sense. But in the quantum sense, the electrons in the metal are described by wave functions that don't stop abruptly at the metal's surface. Their presence bleeds slightly outward. The surface is not a hard boundary for the wave function. It's a region where the probability thins. So, when the tip is close enough, those faint quantum tails overlap. And overlap is enough. A small tunneling current begins to flow across the gap. No contact, no spark, no bridge. Just a whisper of electrons, slipping through a region they shouldn't cross in the classical picture. And the truly astonishing part is how sensitive that whisper is. Because tunneling probability changes exponentially with distance, moving the tip closer by a tiny amount, less than the size of an atom, can increase the current dramatically. Pull it back slightly, and the current falls away. So, the STM can use that current like a tactile sense. It can feel the surface without touching it. As the tip scans across the material, it rises and falls to keep the current constant, tracing the contours of the electron cloud. The instrument builds a map, a landscape, and on that map, atoms appear. Not as little solid spheres, but as bumps and patterns shaped by electron density and quantum structure. In a very real sense, we learn to see the atomic world by trusting the same thing that made tunneling feel strange in the first place. That probability can reach across a barrier, that a boundary is not always a brick wall for a wave function, and that a tiny effect, if it depends exponentially on distance, can become an extraordinarily powerful tool. If radioactive decay is tunneling acting like a clock, then the STM is tunneling acting like a lantern, a way of illuminating what was once invisible. Now, when we turn toward biology, the mood changes again, because it's easy to overclaim here. People love the phrase quantum biology, the way they love the phrase mystery. It sounds like a secret door, so let's treat it with the tone it deserves: curious, careful, and calm. Life is warm, wet, busy, noisy in the physical sense, full of collisions and vibrations. That environment makes fragile quantum effects hard to preserve. In many cases, the world of cells behaves perfectly well under classical chemistry and statistical physics. We don't need quantum romance to understand digestion, muscles, or circulation. And yet, life also depends on the smallest ingredients of matter: electrons, protons, tiny energy differences, narrow barriers in proteins and DNA. At that scale, tunneling isn't an exotic add-on. It's at least a candidate mechanism, sometimes subtle, sometimes meaningful. One of the clearest places it may contribute is in certain enzyme reactions. Enzymes are not just passive catalysts. They are shaped environments. They position molecules with exquisite geometry. They create local electric fields. They guide reactions along certain pathways and make other pathways unlikely. In some reactions, especially those involving the transfer of light particles like electrons or protons, research suggests that quantum tunneling can play a role. Not always, not everywhere, but sometimes in some systems, under some conditions, a proton may move from one site to another, not by slowly climbing a classical barrier, but by tunneling through a small one. The barrier may be narrowed by the enzyme structure. The distances involved may be just right. The timing may allow the tunneling probability to matter. This doesn't mean enzymes are magic. It means enzymes are precise. They sculpt the barrier, and tunneling is exquisitely sensitive to barrier shape. That's an important theme. Nature doesn't use tunneling by wishful thinking. It uses tunneling when the geometry becomes narrow enough, and when the number of attempts is enormous enough, that a small probability becomes a measurable rate. Another area that sometimes comes up is electron transfer in biological systems. In the machinery of respiration and photosynthesis, electrons move along chains of molecules. Those electrons aren't always rolling like beads from one station to the next. In some cases, they can transfer in ways that are well described by quantum models, including tunneling-like behavior across small gaps. Again, careful phrasing matters. The presence of quantum descriptions in biochemistry is not controversial. Quantum chemistry is how we understand bonds and molecular orbitals in the first place. What's more nuanced is whether tunneling provides a significant pathway in specific living processes beyond what a classical approximation would predict. In several cases, evidence suggests it can. And the reason it's plausible is the same reason it worked in the STM: short distances, narrow barriers, and a world full of repeated opportunities. Then there's DNA. DNA is usually presented as stable, dignified, and faithfully copied, a calm archive. But at the atomic level, DNA is also a dance of protons and electrons. The hydrogen bonds between base pairs are not rigid rods, they're quantum systems. Occasionally, a proton in a hydrogen bond can occupy an alternative position, a phenomenon related to what chemists call tautomerization. In some models, tunneling can contribute to these rare shifts. Most of the time, the system returns to its usual configuration. The strange arrangement doesn't last. It's corrected, or it simply fades back. But in a tiny fraction of cases, a rare shift may coincide with replication, and a mismatch can occur. Over immense timescales and huge populations of cells, rare events matter. Here, it's vital to keep the tone grounded. This is not a claim that tunneling causes mutations in a dramatic, direct way in everyday life. Biology has many sources of mutation: radiation, chemical damage, replication errors, and more. But tunneling is one plausible microscopic contributor among several, especially in the realm of proton behavior, where barriers can be narrow and particles are light. There's a gentle humility in that idea. Life does not rest on one mechanism. It rests on a tapestry of mechanisms, some classical, some quantum, many statistical, all patient. And if you're listening late at night, you can let this settle into a simple feeling. Your body is not a classical machine with a few quantum quirks. It is built from matter that is quantum at its roots. Most of the time, those roots average out into the sturdy world you know. But in certain narrow places, certain carefully shaped molecular gaps, quantum behavior can show through, like a fine thread catching the light. And that brings us back to the theme of this whole episode. Tunneling is not rare because it's forbidden. It's rare because barriers are often thick at human scale. When barriers become thin, when distances shrink down to nanometers, angstroms, and smaller, tunneling stops being a curiosity. It becomes a fact you must design around. A fact you can sometimes harness. A fact nature has been quietly using all along. And there's a final soothing thought here, one that keeps the mood gentle rather than unsettling. Nothing about the living world becomes less meaningful when you learn it has quantum threads. If anything, it becomes more finely textured, more exact, more astonishing in its patience. Because even the processes that feel fluid and warm and human are, deep down, shaped by tiny probabilities, repeated so many times that they become reliable. And once we began building smaller and smaller machines of our own, we found ourselves meeting tunneling everywhere until it stopped being optional. For most of human history, we built machines the way we build furniture. Big pieces, clear edges, plenty of space between moving parts. A gear had room to breathe. A switch was either open or closed. An electrical signal traveled down a wire the way a marble rolls down a groove. Reliable, predictable, comfortingly ordinary. But over the last few decades, something subtle happened. We kept shrinking, and shrinking, and shrinking again. At first, miniaturization felt like pure victory. Faster computers, smaller devices, less power, more capability. A whole world carried in a pocket, quietly humming along with your day. Yet the deeper engineers pushed into the tiny scales, the more the universe began to whisper a reminder. You don't get to make matter smaller without meeting the rules that matter lives by. And at the scale of nanometers, one of those rules is tunneling. Not as an exotic party trick, as a practical constraint, as a design problem, as a constant pressure on the edge of every transistor. To feel why, it helps to picture a transistor the way it's often taught in the gentlest form, as a gatekeeper, a little region that can stop electrons or allow them to pass, a barrier you control. In the classical story, that barrier is firm. If the gate is closed, electrons stay put. If the gate is open, electrons flow. The difference between 0 and 1 is clean and crisp, like a light switch on a wall. But now, imagine that barrier becoming thinner and thinner, not because anyone wants it to be fragile, but because we keep asking for smaller devices. We keep asking for shorter distances. And the moment a barrier becomes thin enough, it stops behaving like a strict line in the sand. Because a strict line in the sand is a human idea. A wave function doesn't care about your line. It can fade through it. So, what does that look like in the real world of chips? It looks like leakage. It looks like a transistor that is off, but not perfectly off. A gate that is closed, but not completely sealed. Electrons, described by a probability wave, don't need an open door if the wall itself has become a thin curtain. At large scales, that curtain might as well be a fortress. The tunneling probability becomes so absurdly tiny that you can treat it as 0 and sleep well. But at the scale of modern electronics, absurdly tiny can become merely annoyingly real. And annoyingly real becomes heat, wasted power, and unreliable behavior. This is one of the quiet reasons the old rhythm of Moore's law has slowed, at least in its simplest form. It's not that engineers forgot how to build. It's that they began running into an enemy that isn't a flaw in the manufacturing. It's physics itself. When a component gets small enough, electrons stop behaving like obedient little beads. They begin behaving like quantum objects again. And in the most practical sense, tunneling becomes the universe's way of saying, if you insist on making the wall thinner, don't be surprised when something slips through. There's a strange calmness in that, if you let it be calm. Because it means the problem is not mysterious. It's not spooky sabotage. It's a predictable rule that can be measured, modeled, and sometimes used. In fact, once engineers realized tunneling wasn't going away, they began doing something very human. They tried to turn the problem into a tool. One of the earliest and most famous examples is the tunnel diode, a device that leans into tunneling rather than fighting it. In a tunnel diode, the material is engineered so that electrons can tunnel through a barrier in a way that produces unusual behavior, like regions where increasing voltage actually decreases current. That sounds backwards if you're expecting simple, everyday intuition. But that backwards curve is useful. It can enable extremely fast switching in certain contexts, because the mechanism doesn't rely on slower, classical movement over a barrier. It relies on the quiet immediacy of tunneling. Even if tunnel diodes aren't the centerpiece of your phone in the simplest way people imagine, they represent an important shift in attitude. Instead of begging quantum behavior to disappear, engineers began asking how to work with it. That attitude becomes even more interesting when you move from tunneling as a nuisance to tunneling as a way forward. Because there's a deeper truth about modern computing that rarely gets said out loud. We don't just want smaller devices, we want efficient devices, and efficiency often comes down to energy. How much energy you need to switch a bit. How much energy is wasted as heat. How gently you can guide electrons without losing control. This is where concepts like tunnel field effect transistors, often shortened to TFETs, enter the conversation. You don't need the full engineering blueprint to feel the idea. A traditional transistor, in simplified terms, asks electrons to go over an energy barrier when the device turns on. That tends to require a certain voltage, a certain push. A TFET tries a different approach. It aims to let electrons tunnel through a barrier in a controlled way, which can, in principle, allow switching at lower voltages. Lower voltage means less power. Less power means less heat. And less heat means you can pack more computation into the same space without turning your device into a tiny furnace. That, in principle, matters. Real-world devices always wrestle with real-world imperfections, manufacturing constraints, and trade-offs. But the direction is telling. The future of electronics isn't only about shrinking, it's about learning the most patient way to guide quantum behavior so that it serves stability instead of chaos. And as devices shrink, the story stops being only about barriers and gates. It becomes a story about confinement. Because when you confine an electron to a very small region, so small that its wave nature becomes unavoidable, you don't just get smaller, you get different physics, different energy levels, different behavior. This is where quantum dots enter like tiny beads of controlled possibility. A quantum dot is, in a sense, a small box for electrons, small enough that their allowed energies become discrete, like rungs on a ladder rather than a smooth ramp. That discreteness can be used. In displays, for example, quantum dots can emit light at very specific colors, depending on their size. Not because someone painted them that way, but because the quantum confinement sets the energy difference between levels, and that energy difference sets the color of the photon released. It's one of the softer marvels of modern technology, a TV screen glowing in vivid color because electrons are living in tiny quantum cages, obeying the mathematics of confined waves. And the same general idea, confinement leading to discrete energy behavior, shows up all over nanoscale engineering. At these scales, you're not just sculpting circuits, you're sculpting quantum landscapes. You're shaping which energies are allowed, which are forbidden, and which transitions are likely. You're designing not only with geometry, but with probability. And this is where the emotional tone of the episode can stay gentle rather than frantic. Because nothing about this is a disaster story. It's a realism story. We spent centuries living in a world where classical approximations were enough. They worked beautifully because our tools were large compared to the quantum scales. But now, our tools have become small enough to live near the boundary where quantum behavior is no longer negligible. So we adapt. We build new materials, new structures, new architectures. We stack transistors in 3 dimensions. We use new gate designs. We explore new semiconductors. We search for ways to keep off truly off, and on truly on, without demanding the impossible. And through all of it, tunneling sits there like a quiet constant. Sometimes a leak you must prevent. Sometimes a mechanism you can harness. Always a reminder that electrons do not live inside our metaphors. They live inside quantum rules. There's a particular kind of wonder in the way this plays out. Because in the everyday world, smaller usually means simpler. A smaller version of something feels like a reduced version. But in physics, smaller often means stranger. Not because the universe enjoys confusion, but because the assumptions you've been using stop applying. A thick barrier becomes thin. A definite path becomes a spread out wave. A firm no becomes a probability that is merely low. And when you build at the edge of that reality, you don't just discover new gadgets. You discover new questions. Questions that are surprisingly intimate, considering they live at the edge of the invisible. If electrons can tunnel through a barrier, what is the electron doing while it's tunneling? Does it travel through the forbidden region in any meaningful sense? Does it have a speed there? A time? Or is the whole idea of motion inside the barrier the wrong mental picture? For a long time, physics could predict tunneling outcomes with stunning accuracy without answering those questions in the way our intuition wants. It could tell you the odds. It could tell you the rates. It could build devices and clocks and microscopes. But the inside of the wall remained oddly private. And that is where our curiosity naturally drifts next. Not toward more gadgets, but toward the hidden choreography inside the barrier itself. If you've ever tried to picture quantum tunneling, your mind probably draws the same cartoon every time. A tiny particle runs toward a wall, and then, somehow, it's on the other side. No crack in the wall, no tunnel carved through it, no little door. Just there. And the moment you try to imagine the middle, the moment you try to imagine what happened inside the wall, your intuition gets lost. Because inside the wall is the place classical physics calls forbidden. It's the region where the math says, gently but firmly, this cannot happen. That's why this question has stayed oddly intimate for so long. Not does tunneling occur? We know it does. But something quieter. What does it mean to cross a place you're not allowed to be? In everyday life, a barrier is physical. It's wood, or concrete, or glass. It blocks you because your body collides with atoms, and those atoms refuse to share the same space. In quantum life, the word barrier becomes more subtle. A barrier can simply be an energy hill, a region where, if a particle carried only classical energy, it would roll up partway, slow, stop, and turn around. No drama, no mystery. A marble on a ramp. And yet, when we go down to the scale of electrons and atoms, that energy hill isn't a wall in the same way. It's more like a region where the usual rhythm of motion changes. Outside the barrier, a particle behaves like a wave that oscillates. It has a pattern, a kind of repeating pulse, peaks and valleys like a calm ripple on a pond. But inside the barrier, the wave does something else. It doesn't keep waving the same way. It fades, not instantly, not like a switch, more like a sound moving through a thick door. A voice doesn't slam into the door and become nothing. It becomes quieter, and quieter, and quieter. That's the first strange clue. The inside of the barrier is not a blank void. It's not a place where physics turns off. It's a place where the wave function becomes an evanescent presence, a ripple that cannot sustain its normal rhythm. So, it decays. And decay is not the same as zero. That's the whole story in one soft sentence. A barrier doesn't erase the wave, it dims it. Now, if you're listening in bed, you don't need to hold equations in your mind, but there's one image worth keeping. Imagine the wave function as a kind of probability atmosphere, not a cloud of stuff, a cloud of might. Outside the barrier, the atmosphere can swirl and repeat. Inside the barrier, it thins out, as if the air itself is being gently absorbed. So the deeper the barrier, or the wider it is, the more that atmosphere fades. And here's why the world feels stable at human scale. For a tennis ball, the barrier is unimaginably wide, not just physically, but in every hidden way the quantum math cares about. So its probability atmosphere gets crushed to something like nothing. But for an electron, the barrier can be thin enough that the atmosphere is still faintly present on the far side. Not bright, not likely, just present. And if it is present on the far side, even a little, then tunneling becomes possible. Now we arrive at the 100-year mystery. Because the moment you accept that tunneling is real, the next questions arrive like whispers. Does the particle travel through the barrier, the way a swimmer travels through water? Or does it vanish on one side and appear on the other, like a cut in a film? Is there motion inside the forbidden region? And the strangest question of all, how long does it take? Because time feels like the most trustworthy thing we have. You can doubt where something is. You can doubt what it is, but you don't usually doubt how long it took to happen. And tunneling invites you to doubt even that. For decades, physicists have argued, carefully, patiently, about something called tunneling time. not because they enjoy confusion, but because the concept itself is slippery. In classical motion, time inside a region is easy. You measure the speed, you measure the distance, you divide. But in the forbidden region, the wave function doesn't behave like a traveling ripple with a normal speed you can point to. Inside the barrier, the wave isn't doing its usual marching rhythm. It's fading. So, what does speed even mean there? Some approaches ask, how long does the particle dwell near the barrier? Some ask, how long until probability shows up on the far side? Some ask, if you build a clock into the particle's internal state, what does it register? And here's the part that makes headlines sound spooky. Some versions of tunneling time produce answers that look too fast. Sometimes the peak of a wave packet seems to emerge earlier than you'd expect if it had moved through the barrier at any ordinary speed. This is where people start whispering words like instantaneous, or worse, they start whispering faster than light. But this is one of those places where the universe punishes simplistic thinking. Because that peak is not a tiny marble. It's a feature of a spreading wave packet, reshaped by what the barrier allows through. In many cases, what looks like an early exit is not a message traveling superluminally. It's a filtering effect, like a thick door that muffles low frequencies and lets a sharp click sneak through. If you only listen to the sharpest part, you might think it arrived too soon. But no usable information outruns light. Relativity stays intact. The real mystery remains, quieter than the clickbait. Even if nothing breaks causality, what is happening inside the barrier? Is there a there in there? To find out, you'd like to do the obvious thing. You'd like to watch it, but in quantum physics, watching is never passive. To measure where the particle is while it's tunneling, you have to interact with it. And interaction is not an innocent glance. It is a shove, sometimes gentle, sometimes violent, that changes the very thing you hope to observe. So, the challenge became almost poetic. How do you time an event that happens in a place you cannot look without changing the event itself? For a long time, that challenge was simply too hard, because tunneling can happen incredibly fast. Not in human seconds, not in milliseconds. In the language of modern experiments, we're talking about slices of time so thin they barely fit into imagination. Attoseconds, a billionth of a second. An attosecond is to 1 second what 1 second is to the age of the universe, give or take. It's the time scale where electrons do their quiet work, where chemistry happens, where motion becomes a flicker, and if tunneling time lives anywhere measurable, it lives there. So, in the last couple of decades, researchers began building new kinds of clocks. Not ticking gears, not digital counters, but pulses of light, ultra-short bursts, used like strobe lights for the quantum world. They found ways to set up experiments where an electron is nudged toward escape by a strong laser field, where the act of leaving an atom can be modeled as a form of tunneling, and where tiny shifts in angle and momentum can carry timing information, the way a shadow can tell you where the sun must have been. These are delicate experiments, the type where you can't fully separate the system from the measurement, the type where the answer arrives with uncertainty bars and philosophical caution. And yet, the picture has started to sharpen, not into a simple cartoon, into something stranger and more beautiful. The emerging theme is this: tunneling is not a teleportation trick. It is not nothing, then suddenly something. It behaves more like a choreography of a wave function, an extended object of probability that interacts with the barrier region in a structured way. In some experiments and theoretical descriptions, the under-the-barrier dynamics aren't just a monotone fade. They can include phases, subtle shifts, interference-like behavior. The wave function can, in a sense, self-interact with the geometry of the barrier. And when scientists talk about hidden dynamics, they don't mean hidden in a mystical way. They mean hidden because the normal tools of measurement smear the story. It's like trying to photograph a hummingbird wing with a slow camera. You don't see motion, you see blur, but the blur still contains information. If you build a faster camera, the wing reappears. In mid-2025, some headlines described work from teams, including groups in South Korea and Europe, often cited as involving Postesh and a Max Planck Institute, reporting evidence consistent with richer internal structure during tunneling than the simplest textbook picture suggests. In careful language, the claim is not that we watched an electron crawling inside a wall. The claim is gentler, that when you analyze the data with new methods, when you model the process with more realistic quantum trajectories, you can see signatures that behave as if the electron's probability amplitude is not merely leaking straight through. It may fold into complex paths. It may briefly loop in a way that resembles an under-the-barrier detour. It may even show hints of something like a collision-like interaction with the core region before it finally emerges. Again, this is not a billiard ball bouncing. It's a wave function reshaping under constraints. But even saying that out loud changes how tunneling feels in the mind, because it suggests the forbidden region isn't a magical gap. It's a region with rules. Different rules, but rules. And if those results continue to hold up, the old mystery shifts into a new one. Not does anything happen inside, but what kind of thing is allowed to happen there? Because inside the barrier, the mathematics often uses a peculiar concept, an imaginary momentum. That word, imaginary, sounds like we're leaving reality. But it's not fantasy. It's a sign that the usual oscillation becomes exponential decay. The wave function isn't marching forward in the ordinary way, so the momentum you'd assign, if you force the classical form onto it, comes out with an I in front. That I is not telling you fake. It's telling you different mode. Like the difference between a vibrating string and a slowly settling one. One oscillates, one relaxes, both are real. They just don't look the same. So, when we ask, is there motion inside the barrier? The best answer is not yes or no. It's something softer. There is evolution. There is a change in the wave function across space and time, with structure that can, under the right conditions, leave measurable fingerprints. And in that sense, tunneling isn't a single moment. It's a process, a quiet process. One that can be quick, but not necessarily zero. One that can be probabilistic, but not shapeless. Even the impossible has a kind of internal logic. And once you let that settle, another thought becomes strangely calming, because it means the universe is not cheating when it tunnels. It isn't breaking its own rules and then covering it up. It's following a deeper set of rules, the ones written in waves and probabilities rather than in hard classical certainties. The wall is not a brick that says no. It's a landscape that says, this is unlikely. And this is even more unlikely. And this is so unlikely that you will almost never see it, unless the universe repeats the attempt 1 trillion times, or unless engineers learn to build the conditions on purpose. That is how the world stays steady, and that is also how the world stays possible. Now, if you want one final image to carry into sleep, let it be this. Picture an electron not as a bead, but as a ribbon of probability. As it approaches a barrier, the ribbon doesn't strike and rebound like rubber. It presses into the forbidden region, softly. Its presence fades as it goes in, but it doesn't snap. The ribbon becomes thinner, quieter, more ghost-like. And still, sometimes a faint thread survives on the far side. Not enough to be certain, enough to be real. And when it is real, when it emerges, it doesn't feel like a magic trick anymore. It feels like a rule you didn't grow up with. A rule the universe has been using all along. And here's the turn that makes this mystery feel even bigger. Because if tunneling can have internal structure, if it can have timing on the scale of attoseconds, if it can have choreography rather than pure disappearance, then the question becomes, can this forbidden region behavior ever rise above the microscopic? Can tunneling ever happen in a system large enough to hold and still remain coherent? That is where the story starts to touch the human scale, not in walls and marbles, but in circuits, in superconductors, in the strange, steady world where many particles can move as one. And that is exactly where we're headed next. Imagine taking everything we've said about tunneling, this quiet, unlikely leak of probability through a forbidden place, and scaling it up until it's no longer a story about a single electron. Not a speck, not a lonely particle, but a whole system large enough to sit in your palm, behaving like one patient quantum object? That question used to feel almost rude to ask, because the ordinary world trains you to believe that quantum behavior is fragile, that it belongs to atoms, to tiny gaps, to laboratory whispers, and the moment you make something big, the spell should break, the weirdness should dissolve. But in the late 20th century, a few physicists built a kind of bridge. They didn't try to make a boulder tunnel through a mountain. They did something more clever. They chose a material that already knows how to move as one. A superconductor. In a normal wire, electricity is like a crowd squeezing down a hallway. Every electron bumps. Every vibration of the lattice is another shoulder check. That's resistance. Energy leaking away as heat. A superconductor is different. When it's cold enough, the crowd changes its behavior. Electrons begin to pair up in a way that feels almost poetic. Two partners moving together, not because they like each other, but because the environment makes that partnership stable. These are called Cooper pairs, and the name is less important than the consequence. The consequence is this. Instead of billions of independent particles scrambling through a wire, you get a single coordinated wave, an electrical togetherness that can carry current without the usual losses. It's one of the first hints that the boundary between small quantum and large classical isn't a brick wall. It's more like fog, and in the right conditions, you can walk deeper into that fog than you'd expect. Now, picture two superconductors separated by something that seems, at first, like a deal breaker, a thin insulating barrier, a microscopic layer that says no. This is the famous Josephson junction. Two superconducting regions with a delicate no man's land between them. Classically, an insulator is a stop sign. It's the kind of barrier you trust. Charges can pile up on one side, but they don't simply stroll through. And yet, here is the twist that made history. In a Josephson junction, current can flow anyway. Not by smashing through, not by cracking the barrier, but by tunneling. A supercurrent, a current carried by that collective superconducting wave, can appear on the other side as if the barrier was never fully absolute. And it's hard to overstate how strange that is, because it's not just one electron doing something sneaky. It's a coordinated quantum state, acting like it has a single intention. It is macroscopic tunneling, not because it's the size of a basketball, but because it involves a system large enough to be engineered, wired, measured, and held. When you first hear that, you might be tempted to picture it as a swarm of tiny particles each tunneling on their own, like 1,000 ants slipping through cracks. But the more faithful mental picture is quieter. It's a wave, spanning a whole circuit, and the tunneling is a shift in that wave's whole body configuration. Almost like a compass needle that can point one way or another. Almost like a marble that can rest in one shallow valley or another. This is where the Josephson junction becomes more than a component. It becomes a stage, because the junction doesn't just allow tunneling. It allows the circuit to have distinct, stable states, and to move between them in ways that look eerily like a quantum system you'd normally only draw on a chalkboard. One of the simplest ways to feel this is to stop thinking about the junction as a gate, and start thinking about it as a landscape made of energy. In certain Josephson circuits, the energy can be shaped into something like a series of gentle hills and valleys, places the system can sit and places it shouldn't be able to cross if it were obeying purely classical rules. If the system is trapped in one valley, classical intuition says it stays there unless you give it enough energy to climb out. But quantum mechanics adds a second option. It can tunnel. It can escape without ever cresting the hill in the ordinary way. And when physicists observed that kind of escape happening in real engineered circuits, it was a deep confirmation of a bold idea. Quantum mechanics isn't only about the smallest things, it's about the right things. About coherence, about isolation from noise, about building a system that can hold its delicate phase relationships steady long enough for the quantum rules to show their face. In the 1980s and beyond, experiments with these superconducting circuits did something that feels almost like an answer to a childhood dare. Prove to me that quantum mechanics is real and something I can touch. And they did. They showed that an electrical circuit, made from ordinary-looking components, arranged with extraordinary care, could exhibit quantum tunneling and discrete, quantized energy behavior. Discrete, not continuous, meaning the circuit didn't absorb energy in any amount you pleased. It had preferred steps, specific rungs on a ladder, like a guitar string that doesn't vibrate at just any frequency, but chooses harmonics. This is one of the most calming ways to understand quantization, actually. Because we already accept it in music. A violin string doesn't need to decide to form standing waves. It simply can't do otherwise, given its boundaries. In a similar spirit, a superconducting circuit, under the right conditions, doesn't behave like a smooth, classical reservoir of energy. It behaves like a quantum object with allowed modes. And those modes can be probed, measured, repeated, trusted. That is the word that matters. Trusted. Because when you can repeat a quantum effect in a device, you can build again, wire again, and measure again. It stops feeling like a one-off magic trick. It becomes a tool. It becomes an engineering platform. And that, quietly, is the doorway to the modern quantum era. Now, the mind often wants to ask a very practical question at this point. How can something big stay quantum? Because bigness usually comes with chaos, heat, vibration, stray electromagnetic fields, 1,000 little disturbances that act like constant interruptions. And interruptions in quantum physics are not polite. They don't just add noise. They force a system to lose coherence, to stop behaving like one smooth wave and start behaving like a messy collection of parts. So the secret is not that big things are quantum. The secret is that some big things can be made to behave as a single quantum degree of freedom, if you protect them, cool them, shield them, design them so the important variables are isolated like a candle flame in a glass lantern. This is why superconducting circuits live in environments that look almost ceremonial. Deep cooling, careful filtering, layers of shielding, not because the physics is fragile in a weak way, but because the physics is honest. It will do what the equations say. If you keep the conditions clean, the quantum behavior appears. If you let the environment grab it, the behavior fades. It doesn't break. It simply blends back into the classical average, like a sharp image turning into a blur when you smear it with your hand. In that blur, the world feels normal again. In the sharpness, the world feels almost impossibly precise. And this is the point where the Nobel story starts to feel inevitable. Because what was recognized in 2025 wasn't just an exotic effect. It was a turning point in scale. According to the Nobel Prize's description, the 2025 Nobel Prize in Physics went to John Clark, Michael Devereux, and John Martinis for experiments demonstrating macroscopic quantum mechanical tunneling and energy quantization in an electric circuit. Quantum behavior in a system big enough to hold and wire up, not merely imagine. Even if you never memorize a name, the theme is what matters for your intuition. They helped prove that quantum mechanics could be made visible at the level of engineered hardware. And once that was true, a new question became unavoidable. If we can make a circuit behave like a quantum object, could we make it behave like a bit of quantum information? Not yet. Not easily. But the direction was set. Before we get there, it helps to linger on one gentle detail: why the Josephson junction is so special. A Josephson junction is not merely a barrier. It's a barrier that a quantum wave can partially occupy. And because it sits between two superconductors, two regions with a well-defined quantum phase, it becomes a place where difference matters. In everyday life, phases feel abstract. But in wave physics, phase is simply where you are in a cycle. Peaks, troughs, timing, rhythm. In superconductors, that phase becomes a real physical variable, one that can shift, oscillate, and sometimes tunnel between configurations. So, you can build circuits where the state isn't just the voltage you read on a meter. It's a quantum state of the entire system, a state with discrete energy levels, a state that can be nudged with microwaves, a state that can jump in a way that looks like a particle escaping a trap. And when you watch that jump, you are watching tunneling, without needing to stare into an atom. You are watching it in a circuit. There is something profoundly soothing about that, because it turns the quantum world from a rumor into a craft. It tells you that reality has a hidden layer of rules that are not chaotic and arbitrary. They are structured. They are repeatable. They can be built. And yet, even with all that control, the behavior retains a kind of humility. The probabilities are still there. The maybe never fully goes away. Even in a carefully engineered Josephson circuit, you can't make tunneling happen like clockwork in the way a classical switch flips. You can increase the likelihood, you can shape the landscape, you can prepare the state. But the final moment carries that quantum flavor, a randomness that is not ignorance, but fundamental. And in this context, macroscopic quantum tunneling is not a gimmick. It is a statement about nature. A statement that says, the universe does not enforce classical certainty by size alone. It enforces it by interaction, by entanglement with the environment, by noise, by heat, by the constant gossip of the surrounding world. When you quiet that gossip, when you keep a system from being constantly interrupted, the quantum rules are still waiting underneath, patient, ready, like stars that don't stop shining just because morning arrives. They're still there. They're simply drowned out by daylight. This is why it's fair to say the quantum world doesn't end. It fades, unless we learn how to protect it, unless we build the lantern. And when we do, when we keep the flame steady, we can begin to use it, not as a philosophical curiosity, but as a technology, sensors, clocks, amplifiers, and eventually computation. Because a Josephson junction is more than a historical centerpiece. It is one of the beating hearts of today's most prominent quantum computing approach, superconducting qubits. That's not a promise that quantum computers will replace your laptop next year. It's something gentler. It's an explanation of lineage, a clear ancestry, tunneling through a barrier, made stable in an electrical circuit, made controllable as a quantum state, made useful as a unit of quantum information. And notice what that lineage does to the impossible. It makes it feel ordinary, not in the sense of boring, in the sense of natural, as if the universe has been allowing these behaviors all along, and we are simply learning how to listen without shouting over it. So when someone says, can tunneling happen at human scale? The calm answer is, it already has. It happens in the devices we built in the lab. It happens in circuits you can hold. It happens not because we force nature to break its rules, but because we finally learned which rules were always there. And once we learned that, a new kind of machine stopped sounding like science fiction. It started sounding like engineering, slow, careful engineering, built on a thin barrier that turns out to be, in the quantum world, not a wall at all. There's a moment when the story stops sounding like mystery and starts sounding like craft, not magic, not a loophole, craft. Because once you can build a thin barrier on purpose, and once you can predict what will slip through it, you can begin to treat the quantum world like something you can work with, carefully, patiently, the way engineers work with wind or heat or electricity. And that is where quantum computing enters the room. A normal computer is built on certainty. A switch is either on or off. A tiny region inside a chip holds a definite state, and the rest of the machine reads that state again and again, billions of times per second, with the confidence of a well-worn habit. A quantum computer is built on something softer. It uses a physical system that can hold a blend of possibilities, long enough for those possibilities to interact, and long enough for the machine to take advantage of the pattern they form. If a classical bit is like a coin lying flat on a table, heads or tails, then a qubit is more like a coin you've just spun. It isn't committed. Not yet. It's not that the qubit is both in the everyday sense. It's that the qubit carries a kind of readiness to become either outcome, and that readiness can interfere with itself, like overlapping ripples on a dark pond. That interference is the whole trick. In a quantum algorithm, you don't simply store more information. You choreograph amplitudes, those gentle weights of possibility, so that some outcomes reinforce each other and others cancel out. And in the end, you still measure, You still get a definite answer. The coin lands. But the route it took to get there was not the usual route of classical certainty. It was a route through a landscape of might. Now, here's the part that matters for our story. Many of the most mature quantum computers today are built from superconducting circuits, not from isolated atoms floating in a vacuum chamber, not from crystals balanced on the edge of silence, from circuits, from something that looks, at a glance, almost ordinary, a few patterned metals, a few carefully shaped wires, a few components that resemble the alphabet of electrical engineering. But inside those circuits, at very low temperatures, electricity behaves in a way that feels strangely unified. In a superconductor, current can flow without resistance. And more than that, the electrons pair up and move together in a coherent way, like a crowd that has stopped being a crowd and started being a single wave. If you've ever watched a marching band lock into step, you've felt the intuition. Many feet, one rhythm, many parts, one motion. And at the heart of these superconducting quantum circuits sits a familiar character from our tunneling story, a Josephson junction. Two superconductors separated by a thin insulating barrier, thin enough that quantum tunneling becomes the bridge. In that tiny gap, something remarkable happens. The junction doesn't behave like a plain wire. It behaves like a quantum element, one that can create discrete energy levels in the circuit, like rungs on a ladder. That ladder is what makes a qubit possible. Because if you can build a circuit with two well-defined quantum energy states, you can label them. You can call one state 0. You can call the other state 1. And you can also create controlled mixtures of the two without forcing the system to decide too soon. That's a qubit, a quiet engineered maybe, held in place by a barrier that, in the quantum world, is never perfectly final. But there is a reason you don't have one in your pocket. Not yet, because qubits are delicate. They are not delicate in a poetic way. They are delicate in a practical way, like soap bubbles. They don't like heat. They don't like stray electromagnetic noise. They don't like microscopic imperfections. They don't like the gentle chaos of the outside world. The outside world is loud, and coherence is shy. So, the first era of quantum computing has been, in many ways, an era of learning how to keep the system quiet. Cold helps. It slows thermal agitation. It reduces noise. It turns the world's usual restlessness down to a whisper. That is why many superconducting quantum systems live inside dilution refrigerators, machines that look like golden chandeliers and work like deep winter. But even in that cold, errors happen. A qubit can lose its quantum posture. It can forget the delicate relationship between its possibilities. And the moment that happens too often, your careful interference pattern begins to blur. The computation loses its shape. So, the central challenge of quantum computing has never been simply, can we build qubits? We can build qubits. The central challenge is, can we keep them reliable long enough? And can we correct their mistakes without destroying the quantum information? That last part is subtle, because in the classical world, checking a bit does not disturb it. You can read it, you can copy it, you can back it up. In the quantum world, measurement is invasive. If you measure a qubit directly, you force a definite outcome. You collapse the spun coin. So, error correction in quantum computing has to be more clever. It doesn't read the qubit's secret directly. It checks relationships. It asks questions like, are these two qubits consistent with each other? Does this pattern match what a healthy system should look like? It's more like proofreading a paragraph without staring at any single letter too hard, watching grammar and structure so you can spot when something has drifted. And the big idea is this: if you build a code, an error-correcting code, that spreads one logical qubit across many physical qubits, you can protect the information. You can let individual pieces wobble, while the overall meaning remains intact. This is where the field has been marching, step by step. And in recent updates from major labs, one repeated theme has been especially reassuring. When error correction schemes scale in the right way, the overall logical error can drop, sometimes dramatically, rather than ballooning out of control. You don't need the technical details tonight. The emotional meaning is enough. For years, a fear hovered over quantum computing. What if adding more qubits just adds more ways to fail? What if scale is the enemy? What if the dream collapses under its own weight? Error correction is the answer to that fear. Not a perfect answer, not a final answer, but a direction that feels like solid ground. A direction that says, with the right architecture, more hardware can mean more stability, not less. And if that sounds like slow, careful engineering, that's because it is. Now, take a breath, because we're about to widen the view. One of the reasons quantum hardware looks so exotic is the cold, the refrigerator, the sense that quantum behavior only belongs in deep freezers and delicate labs. But not all quantum platforms rely on deep cold in the same way. Photons, for example, particles of light, can carry quantum information at room temperature. They are already comfortable in the warm world. They don't need to be chilled to near absolute zero to exist. The challenge there is different. It's not about keeping a current from heating up. It's about creating and controlling quantum states of light with high precision and interfacing them with matter in reliable ways. And there too, the trend has been toward devices that feel less like cathedral-sized experiments and more like technology. Smaller, more integrated, more manufacturable. Over the last year or so, researchers have reported progress in nanoscale photonic devices that aim to generate and guide quantum signals in more practical conditions, sometimes even pointing toward room temperature operation for parts of the stack. Not tomorrow in every phone, but enough to soften the boundary. Enough to hint that some quantum capabilities, communication links, sensors, specialized components may gradually move closer to everyday environments. And the field moves fast, which means the headlines and milestones will keep shifting. But the direction is steady, from freezer-sized machines toward devices that feel ordinary. From quantum effects as laboratory curiosities toward quantum effects as engineered tools. And when you zoom out, you can see how tunneling quietly sits beneath it all. A Josephson junction is a tunneling device. It is a controlled impossible, a thin barrier carefully built that becomes a bridge only because the quantum world refuses to be perfectly walled in. So, you can think of modern quantum technology as a family of gentle negotiations with reality. Not demands, negotiations. We don't force particles to behave classically. We don't pretend the quantum world is a myth. We learn its habits. We work with its probabilities. We build devices that are patient enough to let the weirdness do something useful. And we learn, over time, how to protect that weirdness from a noisy universe. If you're listening in the dark and all of this feels far away, let it be far away. You don't have to hold every detail, just keep the shape of the idea. A wall is not always absolute. A barrier is not always final. And the future sometimes is built from things that feel impossible until they start sounding like engineering. Not fast engineering, not flashy engineering. Slow, careful engineering, built on thin barriers, that turn out to be, in the quantum world, not walls at all. And when you're ready, we can let the bigger meaning settle back in. The sun, your phone, and you, all quietly connected by the same gentle rule. The universe can do the impossible, and do it softly. Tonight, we didn't just learn a clever fact. We softened a picture your intuition has held for a long time, that a wall is absolute, that a barrier is final, that matter must obey the simple rule of here or there. And now, gently, that picture has changed. Because in the quantum world, a wall is not a command, it's a question. A thin region where possibility fades, but doesn't always vanish. A place where nature allows a quiet exception, small, patient, and incredibly real. And when you think about it that way, 3 ordinary miracles come back into focus. The sun keeps shining, not by force alone, but by countless tiny chances adding up into certainty. Your phone keeps its memories, not by magic, but by electrons slipping through barriers too thin to be truly closed. And you, right now, are here, breathing. Because the universe has been doing the impossible in the background for billions of years, without ever raising its voice. If this kind of calm wonder helps you unwind, you can gently support the channel by tapping like, subscribing, or leaving a comment. Just a small thought, or even a single word about what you want to drift into next. It helps more sleepy minds find their way here too. But for now, you don't need to hold on to the details. You don't need to memorize the names or the history or the equations. Just keep the feeling. That reality is stranger than we were taught, and kinder than we feared. That even the hardest wall has softness at its edges. That the universe doesn't always choose certainty. Sometimes it chooses probability, and builds everything from that gentle rule. So let your shoulders loosen, let your breathing slow, and let the night do what it does best. Sleep well, curious traveler. Outside your window, the world looks solid and still, but deep beneath that calm surface, the universe is doing the impossible. Quietly. And now, so can you. Good night.